Hello again. Welcome to our third vodcast, which is the second of Chapter 1. There will be 3 vodcasts from Chapter 1 entirely. So this will cover sections 1.4, 1.5, and 1.6. The material in 1.4 and 1.5 is probably somewhat familiar to you. 1.6 may be new. It may be a term that you've heard, viscosity, which we're going to define scientifically and work with in this vodcast. Then our next vodcast will finish Chapter 1. So, starting with Chapter 4, or with Section 4, excuse me, I'm going to go to the document camera. And basically, in Section 4, we define some properties of fluids. And the first that we start with is a property that is probably familiar to you from thermodynamics, perhaps, or from chemistry, and that is the property of density. Density is indicated is represented by the Greek letter rho, and its units in the SI system would be kilograms per cubic meter. And in the U.S. customary system would be slugs per cubic feet. So as you can see, the dimensions are mass per length to the third or mass length to the negative third. Right. So density tells us how much a unit volume of our fluid weighs. Now, we also represent this concept in some different ways. One is called specific volume. And those of you that have taken thermodynamics, you're probably more familiar with this term, where specific volume, which is designated by a small v, is the reciprocal of density, or instead of being mass per length to the third, it's length to the third, or volume, per mass. And then continuing with the idea of specific gravity, where we wish to change from units of mass to units of weight, or dimensions of weight, I should say. We use the Greek letter gamma for specific gravity, and it's equal to gravitational constant times rho. So you can see we have g times mass over volume, or length to the third, and we know that mass times gravity is equal to weight. So those are just 3 different ways to define the weight or mass of a volume, of a unit volume of liquid, or of a gas. But if we, to a gas, we talk about it a little bit, that we have to, and I apologize, this is the specific weight. There we go. The specific gravity actually compares the specific weight of a particular fluid, whether it's a gas or a liquid, to a base. And for liquid, we use the base of water at 4 degrees centigrade. So we take the density of our liquid and divide it by the density of water at 4 degrees centigrade. And for a gas, we usually compare it to air. Now you'll notice that since we have dimensions of mass per length to the third over mass per length to the third, that specific gravity is actually dimensionless. Now, the next concept that we cover in section 1.5 is the ideal gas law. And we've seen this written in many, many forms in chemistry and also in thermodynamics. But basically, some form of the equation looks like this. PV equals mRT, or sometimes it will be written as PV equals N, which is the number of moles, times the universal gas constant times T. Now, the important thing to remember here is that R needs to be used to correct the units. So in other words, there are different values of gas constants that are available to us, but the one that we want to use is the one that works with the other units that we put in. For example, if we use pressure, we could use absolute pressure in atmospheres or pascals or pounds per square inch, and each one of those is going to require a different value of R. Volume could be in cubic meters, cubic inches, liters, mass in units of kilograms or slugs, and temperature has to be in absolute degrees, so it would either be in degrees Rankine or degrees Kelvin. The form of the equation that your authors use in this book is P equals m over v times RT, and as we just learned in section 1.4, mass per volume is density, so they write this equation like this. Pressure is equal to density times the gas constant times the absolute temperature. Now, it is important to note that this only applies to gases. This is not valid in any way for liquids. The reason for that is gases are compressible, so that this relationship between pressure and temperature is somewhat a direct proportion. That is not at all true for a liquid, and I'm sure you can visualize this, is that if you increase the pressure on a liquid, the temperature is not necessarily going to change, and if you increase the volume of if you increase the pressure on a liquid, you're also not going to increase the volume. So the relationship between pressure, temperature, and volume for a liquid is not as directly as it will be for a compressible fluid such as a gas. So if you're using the ideal gas law, your textbook has many values of the universal gas constant, and you just need to look in the tables to find out which one is going to be applicable for your particular set of units. And remember that temperature has to be in degrees Rankine or Kelvin, and actually the pressure has to be in absolute units as well. Okay. So then, for section 1.6, the new topic, which is viscosity. You may have heard this term before. Viscosity refers to the resistance of a fluid to flow. And as you can imagine, or as you may already know, this is highly temperature dependent, and this relationship can be different depending on the type of a fluid. So, for example, you may have heard the expression molasses in January. That means molasses, when it is cold, is quite thick, and that refers to its viscosity. It's not really a thickness in the sense of a density, it's just a resistance to flow. So what we're really getting into is this idea of a shearing force or a shearing stress. And it's how the fluid responds in relationship to that, or in other words, how much of some sort of a force is required or a stress is required to create a change in the shape of the fluid. So as you can see, if you have a solid material, a little block, for example, it doesn't flow at all. So its resistance to flow is somewhat total. There are other fluids that are very thick. Sometimes glass can be approximated as a fluid. It's really more of an amorphous solid, but there's some validity to thinking about that. Or you can think about glue. Glue, before it sets up, is a lot less viscous than it is after it begins to set up. So when we talk about viscosity, that's the idea that we're talking about. Now, to define it mathematically, one way that we describe this behavior is if we take two plates, so maybe this could be two microscope slides, for example, and you put a fluid between them that has some depth B, and if you pull on the upper plate with some velocity U, what you'll find is that an element of the fluid, which was previously just was perpendicular to both plates, as you pull the top plate at some velocity, the fluid will deform in such a way that the fluid near the top plate moves some distance compared to the fluid at the bottom plate. So you can probably also guess that there's some relationship. It's a linear relationship sometimes. In this particular example, it's a linear relationship that defines how this looks. So what we look at then is two different variables. We call one gamma, and we call one tau. And these go along with the variables u and b and y. And if we say that gamma is the shearing strain, which is some sort of an angular displacement based on tau, which is a shearing stress. And if we further take shearing strain and take its first derivative with respect to time, if this is some sort of angular displacement, this must be, the shearing strain must be, the rate of shearing strain must have a time factor involved in it as well. And what we find is that in some way the shearing stress is proportional to the rate of shearing strain. And from our picture, we can also see that the shearing stress is proportional to the rate of change of velocity over, this is u, that's poorly drawn, but u, du, dy. So in other words, as we go from here to here, as y increases, the u, the small u of our velocity, the velocity of the fluid at that location, also increases, and that we have a linear proportionality in this particular case. Well, in order to make this an equation, we define this proportionality as the variable mu, and mu is defined as the viscosity. So mu is written like this. It's a Greek letter, and previously we have used it as a coefficient of friction in statics, perhaps. So in your textbook, there are different diagrams. There's a diagram on the bottom of page 17, for example. Let me slide this over. That shows you the viscosity for some different fluids. So what you see on the x-axis is the rate of shearing strain, which would be du dy, or gamma dot. And here we have the shearing stress, tau. And so if you look at the equation that we've constructed, you can see from the form y is equal to mx plus b, that if b, or the y-intercept, is 0, that the slope of these lines is the viscosity. So you can see the slope of crude oil at 60 degrees Fahrenheit is quite a bit larger than the slope of water at 60 degrees Fahrenheit, which is somewhat larger than water at 100 degrees Fahrenheit, which is quite a bit larger than air. And typically, gases have very low viscosity. So in each of these cases, the viscosity is the slope of that line. Now, the relationship is not always linear. And on the next page, they show some diagrams of viscosity relationships that are not linear. And they also show a Bingham plastic, which, as you see, does not have a y-intercept of 0. That means that there's some, even if you have a rate of shearing strain of 0, there's a shearing stress that is not equal to 0. Fluids that follow a linear relationship with viscosity are referred to as Newtonian fluids. And fluids that bend this way, in other words, it takes more of a rate of shearing strain. If you look at this relationship, you have to put more shearing stress on it to get it to start moving, but then it sort of balances out. That's called a shear thinning. And the opposite effect is called shear thickening, where I guess the best way to think about this is when you start to apply some sort of a velocity or change in velocity to that fluid, it doesn't respond by resisting very much at first, and then that resistance increases. Whereas with a shear thinning fluid, that opposite effect is observed. So there are some strange fluids that behave this way. And anything that is not a straight line going through 0 is sort of collectively called a non-Newtonian fluid. And the relationship, the rate of shearing strain versus the shearing stress relationship is referred to as the rheology of the fluid. It's also referred to rheology for a Newtonian fluid, but it's not very interesting. The other ones are a little bit more interesting. But you can see from the work that we've done so far that if this is, if du dy is basically a linear relationship that, and tau is a linear relationship with that, then mu is going to be a constant over some range of behaviors. All right, so getting to that point, that gets us through section 1.6, and I'd like to work a problem for you. I'm going to work problem 145 in your textbook, and then you are going to be able to continue with your homework problems. And the homework, of course, is put up on our wiki space, so you'll be able to take a look at that. All right, one thing I need to also discuss is there are two different types of measurements for viscosity. One is called the kinematic viscosity, and one is called the dynamic viscosity. And the difference between them is the density of the fluid. So if you look at the inside front cover of your textbook, you'll see that these two values have different sets of units, obviously. If they're different by density, you would expect that. But dynamic viscosity is the one that we refer to just as general viscosity as mu, and kinematic viscosity has a scrolly V, which is the Greek letter nu. So kinematic viscosity is designated by this letter, nu, and dynamic viscosity is designated by this Greek letter, mu. All right. And the relationship between them is that mu is equal to nu times rho, or kinematic viscosity is equal to dynamic viscosity multiplied by the density of the fluid. All right, so obviously they're not going to have the same units, and also you can see density is not always constant, is it? In other words, if you have a gas, for example, and you heat it up, the density of that gas becomes less. So this relationship has that proportionality as well. All right, so problem 145 asks us, it tells us that the kinematic viscosity of oxygen at 20 degrees centigrade and a pressure of 150 kPa, and it does specify that that is in absolute units, which is good. Otherwise, we would have to add in the atmospheric pressure. If that were a gauge pressure, we'd have to add atmospheric in order to find out what that value is. it tells me that the kinematic viscosity is equal to 0.104 Stokes. Now the basic unit for kinematic viscosity is Stokes, which is a huge unit, so it's often reported in centistokes. And from your, let's see, 100 centistokes, okay? So 1 stoke is 100 centistokes. Now, what that means is that, generally speaking, this unit is too large to work with. And for most fluids, if you report kinematic viscosity dynamic viscosity. Did I write that down backward? Let me double check. Yep, kinematic. I was looking at this and I was like, that cannot be right. This is V and this is mu. All right, so we have, rather than what I wrote here, we have dynamic viscosity is equal to kinematic viscosity times density. All right, so that means that the kinematic viscosity is, I keep wanting to do that symbol, the kinematic viscosity is 0.104 Stokes. Now, mu, or dynamic viscosity, then is going to be related by that times the density. All right, so we are given our value of kinematic viscosity, and we wish in this problem to find the dynamic viscosity. So that means we need to find rho, don't we? Well, how can we find rho? Well, first of all, this is oxygen, and at 20 degrees centigrade and 150 kPa. That is most likely, if it is a gas, we could use the ideal gas law. So we could say then that P times V is equal to mRT, or P is equal to M over V is rho RT. And solving for rho, we could say that's equal to P over R times T. All right, so if we use the values that we're given, we're told that this is 150 kPa, which a Pascal is a Newton per meter cubed. So if we reduce it to base units, this would be the K, the kilo, Newton per meter cubed, divided by an appropriate gas constant, and then divided by the temperature, which in this case is 20 degrees centigrade. And to convert that to degrees Kelvin, we need to multiply by kelvins. Or we need to add 273, rather, excuse me. So in your textbook, in the appendices, we can find units for the gas constant, R, that will be appropriate to this particular discussion. So let's take a look. And let's find the gas constant. Gas constants for common gases this is just in your index. Gas constants for common gases, page 14. Let's see if we can find one that's usable for us at that point. Okay, the gas constant R, it just refers to it here, but it tells us that the values are listed in tables 1.7 and 1.8, which in this textbook tell me are the inside front cover of the textbook. All right, so turning to that page, we find some universal gas constants, or it's not universal, but gas constants over here. And we're told in this problem that we are dealing with oxygen, all right? And so our gas constant, excuse me, we could use the gas constant for oxygen, which is 2.598 times 10 to the second times E, okay? Or times E, right? E to the second, so just the exponent. So my number is 2.598 times 10 to the second. My units are joules per kilogram Kelvin. Okay, and that would be my density, and I need to see what that actually boils down to. Because with these problems, especially when you're working with fluids, just like in thermodynamics, for those of you that have taken thermo, you need to be extremely careful to make sure that your units come out properly, because you can get an answer, and if you do not have, if you don't have a good set of units, the answer is not particularly meaningful. Okay, so if we use that 2.598 times 10 to the second in units of joules per kilogram Kelvin, what we find for our density is that the kelvins cancel out, and we have to think about what is a joule. A joule is a Newton meter, so we have newtons cancel out. We then have we have a meter here, and this is meter squared, sorry about that. So then we have meter cubed, kilogram per meter cubed, which is a good unit for density, isn't it? Here we have kilogram in the denominator of the denominator, and we have meter squared times meter, which is meter cubed, remaining in the denominator. And if we do the math on that problem, the value turns out to be just under 2 kilograms per meter cubed. 1.97 kilogram per meter cubed. All right, so we're told that our kinematic viscosity is 0.104 Stokes. And if you refer to your book to find units, you'll find that a Stoke has dimensions of a centimeter squared per second, excuse me, units of a centimeter squared per second. So it's length squared per time. So using our equation then, we know that mu is equal to density times nu, and we know that our value of density is 1.97 kilogram per meter cubed, and our value of kinematic viscosity is 0.104 centimeters squared per second. And one thing that you can see at this point is that you have meters to the third and centimeters squared. So we need to convert one to the other. And it's always better to go into meters because meter is a base unit. So we know that we have 100 centimeters per meter. But since we're squared, we have to square both of these. So we actually get 10 to the fourth in the bottom, which is 10 to the minus fourth up above. So our mathematics goes 1.97 times 0.104 divided by 10 to the fourth. And our value of mu then is 2.05 times 10 to the minus 5. And my units are going to be kilograms. So this cancels this. I have meters squared, so it's over meters seconds. So our units are kilogram meter per second. And if you refer to your book, you'll see that this is usually reported in Newton second per meter squared. So if we go back to Newton's second law, force is equal to mass times acceleration, kilogram meter per second squared is a Newton, or a kilogram is a Newton second squared per meter, and I substitute that here, I get Newton second squared per meter times meter second, and this cancels this, and I'm left with Newton second per meter squared. And that's a good unit for dynamic viscosity. Now, there's one other thing that I want to show you in terms of units for dynamic viscosity, because there's a different value of a unit, which the kinematic viscosity, of course, is a centistoke, and dynamic viscosity is measured in actually, well, it's in, let me do this, it's called a poise. All right, so if you look at a poise is a very large unit of viscosity, but it's abbreviated by the capital letter P, and it's a kilogram per meter per second, or a Pascal second, which, if you think about it on our screen, let me go back to this. I'm going to write this down. Equals Pascal second is 10 poises, and the plural is poises. So if we go back to our document camera, what we can see, a Pascal, we know, is a Newton per meter squared. So we could say that this is a Pascal second, and so we can also say that that's equal to 10 poise. So that's another unit that we can use. So we have our value here as 2.05. Let's do this. 2.05 times 10 to the minus 5, which we have decided is a Pascal second. And we know that 1 Pascal second is 10 poise. So if we do the conversion on that, we could also write that as 2.05 times 10 to the minus 4 poise. And a poise is the more commonly used unit for dynamic viscosity. It's also huge, and just like stokes are generally not used, we usually report kinematic viscosity in centistokes. We usually report dynamic viscosity in centipoises. So 100 centipoises equals 1 poise. All right? Now, it's also been brought to my attention that if we were speaking French, we would pronounce the word poise pois, and I have looked this up. I've visited with many people about it, and I've never heard anybody in the scientific community who supports the use of the pronunciation pois, at least in the United States. But if you hear it pronounced that way, that is the reference. All right, so you have your homework for sections 1.4 through 1.6, and we'll get started with 1.5 through the remainder of chapter 1 on our next podcast, podcast number 4. See you then.